12.3 Lesson 4, Projectile Motion. The objective for today's lesson is, given two of the three initial conditions. The initial conditions refer to the initial height at which the projectile is launched, the initial speed at which the projectile is launched, and the initial angle of elevation at which the projectile is launched. Given two of these three initial conditions, you'll be able to form and solve a system of equations using the given information in the problem, and you will solve this system of equations to find the missing initial condition, because at the beginning of the problem you have 2 out of 3, and then you will have to find the missing initial condition. Once you have all 3 initial conditions, you can write the position vector for the object in projectile motion, and then use it to answer questions about the projectile, questions such as the maximum height, the range, etc. And as we've already seen, this is, of course, the position function for an object in projectile motion in terms of the initial height from which the object was launched, the initial speed at which the object is launched, and the initial angle of elevation at which the object is launched. So you have the position of the projectile as a function of time since it was launched. You have the horizontal component of the projectile's position as well as the height of the projectile's position as a function of time since the projectile was launched. We begin with number 27. A baseball hit 3 feet above the ground leaves the bat at an angle of 45 degrees and is caught by an outfielder, and so on. But if you read the first 2 lines here, you see that 2 of the 3 initial conditions is given. The baseball is hit 3 feet above the ground, so the initial height is 3 feet, and the angle of elevation at which the ball is launched when it was hit by the bat is 45 degrees. But you'll notice that we don't have the initial speed. So our objective is to find the initial speed so we can write the position vector for the baseball as a function of time since it was hit. How will we do that? We need to use what we know, which is that the height was 3 feet and the angle of elevation was 45 degrees, and whatever other information we're given. So we know that the baseball is caught by an outfielder 3 feet above the ground and 300 feet from home plate. What is the initial speed of the ball? And of course we need that to be able to write our position vector. And then once we have our position vector, we can answer the question, how high does it rise? So we know h is equal to 3 feet. We also know theta is equal to 45 degrees. And since we're measuring height in feet, the value of g will be 32 feet per second squared. Knowing all of that, I can write r of t, but of course I don't know the initial speed, so I'll just have to leave that as v naught, and I need to find that to complete my model. So I have v naught times cosine of theta, cosine of 45 degrees, times t I plus h, the initial height is 3 feet, plus v naught, which I need to find, times sine of 45 degrees, times t, minus 1/2 times g. G is 32. Half of 32 is 16. So minus 16 t squared j. So this is what I'm able to do, but my model is not complete because I don't know what the initial speed is. So the first thing that I need to do is figure out the initial speed, and then once I have that, my model will be complete, and I can use it to answer the question, how high does the ball rise, similar to what you saw with example 6 in the previous lesson. Before doing anything else, we can simplify a little bit here. Because we know cosine of 45 degrees, it is square root of 2 over 2. So we can write v naught square root of 2 over 2 times t I plus 3 plus, again, sine of 45 degrees is square root of 2 over 2. So we have v naught square root of 2 over 2 t minus 16 t squared j. If you look at our objective, given two of the three initial conditions in our problem, we're given the initial height and the angle of elevation, you will be able to form and solve a system of equations using the given information to find the missing initial condition so that we can complete our projectile motion model and then use it to answer questions about maximum height, etc. So what given information do we have in the problem that would allow us to write a system of equations and then solve it to find the initial speed? The given information we have is this. A baseball hit 3 feet above the ground leaves the bat at an angle of 45 degrees. We've already used that. But the given information that we want to focus on now is this. This baseball is caught by an outfielder 3 feet above the ground and 300 feet from home plate. So somehow we need to use that to write a system of equations that would allow us to solve for the initial speed at which the baseball was launched. Once we have that information, we can complete our position vector, and then we can use it to answer the question of how high does it rise. So what we need to do now is the following. This baseball is hit, and then at a later time, it is caught by an outfielder, and we know where the catch is made, 3 feet above the ground and 300 feet from home plate. But we don't know the time at which this is happening. We know it's after the ball is hit, but at what time does this happen? We don't know. So that has to be represented with the variable, and I will do it as follows. So we will let the unknown time be represented by t sub 1. Let that be the time at which the baseball is caught by the outfielder. Since we do know where the baseball is caught, we may write the following. We may write that the position of the baseball at the time it is caught by the outfielder, it was caught by an outfielder 3 feet above the ground and 300 feet from home plate. So by the time the outfielder catches it, the baseball has traveled 300 feet from home plate, or a horizontal distance of 300 feet. And the outfielder catches the baseball at a height of 3 feet above the field. So the height of the baseball at t sub 1 is 3 feet above the field. So we know that. So now, how do we get our system of two equations? Well, here's what else we know. This is our partial model for the position vector. So if we evaluate that at the time at which the baseball is caught, it should have the same position that we know about from the problem. But let's go ahead and substitute t sub 1 in place of t in our model. So we will have as follows. So the horizontal component will be v naught square root of 2 over 2 t sub 1 I, and the vertical component will be 3 plus v naught square root of 2 over 2 t sub 1 minus 16 t sub 1 squared j. So now, how do we form our system of two equations in two unknowns? Because these are positions at the same time, the ball is at the same place. So you can set the horizontal components equal to each other. That will give you one equation. You'll get v naught square root of 2 over 2 t sub 1 is equal to 300. And then you will set the vertical components equal to each other. And that will give you a second equation. And that's how you get your system of two equations. So here we have our first equation, and here we have our second equation. You can see that I have a system of two equations and two unknowns. The two unknowns are the time at which the outfielder catches the ball, represented by t sub 1, and of course what I really want, which is the initial speed at which the ball is hit. And I need that to complete my model. So how would I solve this system of two equations in two unknowns? By using the substitution method. This is a somewhat easier problem than what you might usually encounter, and the reason for that is the following. You can see that in our second equation, which is this one here, you can see that I have v naught square root of 2 over 2 times t sub 1. And of course this is exactly v naught square root of 2 over 2 times t sub 1. So I can just substitute this particular quantity with 300 in my second equation. And also you will notice that I have 3 on both sides of the second equation. So if I subtract 3 from both sides of the equation, I will have 0 is equal to this term, which I can replace with 300, minus 16 t sub 1 squared. And that's exactly what I've done to get this particular line. So now I have one equation with one unknown, and I can solve for that unknown, which is t sub 1. So to solve for t sub 1, I can subtract 300 from both sides of the equation, leaving me with negative 300 is equal to negative 16 t sub 1 squared. Divide both sides of the equation by negative 16 to get 18.75 is equal to t sub 1 squared. And so t sub 1 is equal to the square root of 18.75, or approximately 4.33 seconds. But I still need to solve for v naught. How will I do that? Now that I know t sub 1, all I need to do is take the t sub 1 value that I just found and substitute for t sub 1 in the other equation and solve for v naught. And here is my work for doing exactly that. So we are going to substitute for t sub 1 the square root of 18.75, and you see that right here. And now we will be able to solve for v naught in this equation, which is the first equation. And when you solve for v naught using algebra, this is what you get. Approximately 97.98 feet per second. This is the initial speed of the ball. So now I know the initial speed of the ball. And that is very useful because now I can write my position vector for this object in projectile motion. And then use that to answer the question, how high does it rise? So let's go ahead and write our position vector. We're going to write r of t is equal to v naught, so that's 600 divided by the square root of 37.5 times the square root of 2 over 2 ti plus 3 plus v naught is 600 over square root of 37.5 times square root of 2 over 2 t minus 16 t squared j. This is my position vector for this baseball. And of course you can simplify. 2 goes into 600 300 times, so you could write that as 300 times the square root of 2 over the square root of 37.5, and you could do the same here. That's my position vector. So how do we use this to answer the question, how high does the baseball rise? This becomes like example 6 that we looked at in the previous lesson. So what we need to do is we need to look at the vertical component of the position vector. And to answer the question of how high does the baseball rise, we want to know what the relative maximum of the vertical component of the position vector is. So to do that, we will find the derivative of the y component. We will set the derivative equal to 0 to find critical numbers. And then we will determine whether we have a relative maximum or a relative minimum at the critical number. We will have a relative maximum. And then we will evaluate the function at the critical number to find the maximum of this function, which will be telling us how high the ball rises. So this is the y component of the position vector. So we need to begin by finding the critical numbers of the y component of the position vector. So we find y prime. So we take the derivative of each term, and this is what we have. And then we set the derivative equal to 0 to find the critical numbers. So we would add 32t to both sides of the equation, and we solve for t by dividing both sides of the equation by 32. This is what we have for the time. It is approximately 2.165 seconds. And then you can verify that on the interval before 2.165 seconds, from 0 to 2.165 seconds, you can verify that the sign of y prime is in fact positive, which means the heights are increasing. And then after that, you can choose a time slightly after 2.165 and verify that the sign of y prime is negative, which means the heights are decreasing. So by the first derivative test at this point in time, the function y of t must have a relative maximum. So we can find that relative maximum by evaluating the function y of t at this time of 2.165. And when you do that, you get about 78 feet. So the ball rises to a maximum height of about 78 feet at this time. A shot fired from a gun with a muzzle velocity. This is our next problem, number 37. A shot fired from a gun with a muzzle velocity of 1,200 feet per second is to hit a target 3,000 feet away. Determine the minimum angle of elevation of the gun. So when you read this problem, we have one of the three initial conditions. We have the initial speed at which the gun was fired, or at which the bullet leaves the gun, 1,200 feet per second. We really need to know the other two initial conditions. What is the initial height at which the shot was fired, and also the more significant one is the minimum angle of elevation of the gun. In other words, what is the angle at which the shot should be fired so that it will actually hit the target that's 3,000 feet away. So we know one of the three initial conditions. So to make this problem solvable, you do have to make an assumption as follows. If we make the assumption that the height of the target is the same as the height at which the shot was fired, then this problem becomes solvable. We can actually find the minimum angle of elevation that is needed for the shot to hit the target. So you can see from my diagram that I'm sketching that here we have the gun, and this is where the projectile is launched. So this is the initial height above the ground. So here's the ground. So the initial height above the ground is not known. It's probably something like 4 or 5 feet. But it doesn't really matter because our assumption is whatever that initial height above the ground is, the target is at the same height. So we're assuming that the target is at the same height. So you can call that h naught. So h naught would be the initial height, and that is also the height of the target by our assumption. So what we want to find in this problem, we know the initial height now by assumption. We also know the initial velocity, 1,200 feet per second. So the third initial condition that we're looking for is the initial height. Not the initial height, but the initial angle of elevation of the shot. What is that angle? What is the minimum angle of elevation required so that the bullet will actually hit the target, which we know to be 3,000 feet away? So let's read the problem again. A shot fired from a gun with a muzzle velocity of 1,200 feet per second is to hit a target 3,000 feet away. Determine the minimum angle of elevation of the gun. So going back to our objective, given 2 of the 3 initial conditions, you'll be able to form and solve a system of equations using the given information in the problem to find the missing initial condition. So similar to what we did for number 27, we will use the given information to write a system of equations. In this problem, the given information is that the target is 3,000 feet away. And the height of the target, we are assuming, is the same as the height at which the gun was fired. So determine the minimum angle of elevation of the gun. So we don't know the time at which the bullet will hit the target. So that's the other unknown. In addition to the angle of elevation being an unknown, the other unknown is the time at which the bullet will hit the target. So let's specify that. With this, we can write the following equations. R of t sub 1, the position of the bullet at the time it hits the target, will be equal to, using the position vector, v naught, the initial speed, which in this problem is known to be 1,200 feet per second, times cosine of theta, and we're looking for the angle at which the shot needs to be fired, so that's unknown, times t sub 1, t sub 1i, because we're writing this position vector for the time at which the bullet will hit the target. So I use t sub 1 in place of t, plus h naught, which would be the height of the target, same as the initial height at which the bullet was fired. So we're assuming, again, that the initial height of the bullet is h naught, same as the height at which the target is hit. So the initial height by assumption is h naught, whatever that may be, plus v naught, which is known to be 1,200 feet per second, times sine of theta, and theta is what we're after, times t sub 1, minus 1/2 times 32 feet per second squared, so minus 16 t sub 1 squared j. And what else do we know? We know how far the target is from where the shot was fired. We know that the target is 3,000 feet away, so at the time the bullet hits the target, the bullet would have traveled a horizontal distance of 3,000 feet. So that's the position of the bullet at the time t sub 1 when it hits the target. We also know that the height of the target by assumption is the same as the initial height at which the bullet was fired, so it would be h naught by assumption. So now we have enough information to be able to write a system of 2 equations and 2 unknowns. The bullet is at the same place at the same time, so we can set 3,000 equal to 1,200 times cosine of theta times t sub 1, and we can set h naught equal to h naught plus 1200 times sine of theta times t sub 1 minus 16 t sub 1 squared. So here is our system of equations. And if you solve, and our objective is of course to solve for theta, because that's the question in the problem. Determine the minimum angle of elevation of the gun that is needed for the shot to hit the target. To do so, we will solve this system of two equations and two unknowns. The two unknowns are t sub 1, the time at which the shot will hit the target, and theta, the angle of elevation at which the shot must be fired. H naught, if you subtract h naught from both sides of the equation, it will go away. And you just get 0 is equal to 1200 times sine of theta times t sub 1 minus 16 t sub 1 squared. So how do we solve this system of two equations and two unknowns? By using the substitution method. So we can solve for t sub 1 in the first equation by dividing both sides of the equation by 1200 times cosine of theta. And 600 goes into 1200 two times, 600 goes into 3000 5 times. So you get t sub 1 is equal to 5 over 2 times cosine theta. What we're going to do next is take this and substitute for t sub 1 in our other equation. This is called the substitution method, and we're doing the substitution for t sub 1 in the other equation and solve the other equation for theta. So let's take a look at the work for that. So we substitute for t sub 1 in the other equation. Here we have to square that quantity. So 5 squared is 25, and in the denominator 2 cosine theta squared would be 4 cosine squared theta. Again, when you look at this equation now, you see one unknown, and that one unknown would be theta, and we need to solve for that. So how will we solve for that? Usually, you may have to resort to the quadratic formula. Have it in the form a, the square of the quantity that you're looking for, plus b times the quantity that you're looking for, plus c. Set that equal to 0. Use the quadratic formula to find what the quantity you're looking for is equal to. And in problems like these, it will be perhaps something like tangent of theta. So you would find what tangent of theta would be equal to. And then to find theta, you have to use the arctangent function to find theta. Normally, you would probably have to resort to that particular way of solving such an equation as you see here. But in this particular problem, we're able to take advantage of a trig identity so that we're able to avoid having to use the quadratic formula. So let's see how that's done here. So you're going to divide 16 by 4. You get 4. 4 times 25 is 100. So you get minus 100 over cosine squared theta there. And then here, of course, you have sine theta over cosine theta, which you can write as tangent theta. 1200 times 5 divided by 2 is 3000. The next step would be to add this term to both sides of the equation. And I have 100 over cosine squared theta is equal to 3000 times tangent theta. And then I can multiply both sides of the equation by cosine squared theta. And when I do that, I get this line. I rewrote tangent theta as sine theta over cosine theta so that I can simplify by canceling the cosine theta in the denominator with one factor from cosine squared theta. That leaves me with 100 is equal to 3000 times sine theta times cosine theta. As I'm looking at 3,000 times sine of theta times cosine theta, I remember a double angle formula from trigonometry. 2 times sine theta times cosine theta is equal to sine of 2 theta. So I decide to use that. So I will rewrite 3,000 as 1,500 times 2 so that I can have 2 times sine theta times cosine theta, which I can replace with sine of 2 theta. That leaves me with this equation. Again, my objective is to find theta, the angle at which the bullet must be fired for it to hit the target that's 3,000 feet away. So my next step is to solve for theta, and to do that I will begin by isolating sine of 2 theta. So I divide both sides of the equation by 1,500. That leaves me with sine of 2 theta is equal to 100 divided by 1,500, or 1 over 15. So how do I find theta? I need to find 2 theta first, and I can find 2 theta by using the inverse sine function. So take the arc sine of both sides of this equation, leaving me with 2 theta on the left side and the arc sine of 1 over 15 on the right side. But I don't want 2 theta, I want theta. So the last thing for me to do is to multiply both sides of the last equation here by 1/2, leaving me with theta on the left side is equal to 1/2 times the arc sine of 1 over 15, which you can use your calculator to solve. You can either get the answer in radians or in degrees. In degrees, the angle of elevation at which the gun must be held so that the bullet will hit the target 3,000 feet away is about 1.911 degrees above the horizontal. So today we looked at a couple of problems where you're given 2 of the 3 initial conditions from initial height, initial speed, and angle of elevation, and you had to form and solve a system of equations using other given information from the problem to find the missing initial condition so that a position vector for the object in projectile motion can be written. And you can use that to answer other questions about the projectile, such as in our first problem, finding the maximum height of the projectile.